So the next speaker is wrapping everything up, and it's a soulmate of mine, Joe. It's not just soulmate, but it's also my name mate because we have the same name. Just Joe is my English version of my name. Yours is. So yeah, Joe Kiniry is the founder and CEO and chief scientist of Sigilogic, and that's a new startup. Before Joe was leading formal verification activities at Galois, one of the leading R&D companies in the US. So he's a computer scientist and PhD in research in training, and was also in academia with 3 decades in formal methods and high assurance systems, who's bringing theorem prover rigor directly into practice of systems modeling. So this is really incredible. And Joe, the floor is yours. We're excited to see all the magic that you have to share.
Thanks so much. Good morning, everybody. Long day, thumbs up. Wow, that's a lot of thumbs up. I feel blessed. Thanks for having me here. It's a tough act to follow, following Cole and all the things they've been doing at Andrel, which I happen to have been seeing for some time. My name is Joe Kiniry. Indeed, I've started and am running a new company called Sigilogic for the last several months. So I'm going to tell you a little bit about what's going on there. But some of what's in my talk is also discussing a case study, which is public, that you can learn more about what the kinds of things we do, which is coming from my other company, which is called Free and Fair, which is a public benefit corporation, which essentially uses formal methods for matters related to trustworthy elections. In both Sigilogic and Free and Fair, we do a ton of systems engineering, and of late that means working with Symmetry and using Seaside and such. But part of what my talk is about, or a big part of what my talk is about, is a bit of a historical reflection on how we got to where we are today from the point of view of systems engineering. And it's meant to give all of us some inspiration and historical perspective so that we can do things like you've seen in other talks, with other people and with ourselves in a more rigorous, um, uh, but fast-paced fashion, as it were, much as you've seen from Andrel. So my talk is called System as Code at Agent Speed, and what I'll be recapping is sort of 30 years of systems engineering and systems modeling and how we got to where we are today, which is in essence at Sigilogic using dozens of different formal methods combined with systems engineering to not just build systems, but to build systems that are complicated, fabulous national security systems, nationally critical infrastructure systems, or everyday systems wherein we're not just crossing our fingers and hoping we're building the right thing, but we know we're building the right thing. And we have evidence of such that is both driven by and coupled to testing, like you just saw with Andrel, but also with formal verification, but in such a way that you don't have to learn what formal verification is. So let me give you a recap where I or we have come from so that you understand where we are today so we can be extra excited about this world we now live in. I did a couple of degrees at Caltech a long time ago, and my master's thesis was focused on systems engineering. And in those days, this was before SysML existed. This is before UML existed. I was friends with the community of people who did what you would call classic object-oriented modeling or systems engineering in sort of the Stone Age days. So this is early 1990s. And in those days, there was a bunch of different methods that existed that permitted one to write down at a high level what you meant to do. And some of them were very informal, and some of them were very formal. The formal ones didn't often get understood or adopted. They were used by, solitary research groups. These would be things like the Larch language or the Pi language, or formal methods like Z and VDM and B, which were trailblazers at the time, but were all essentially designed by mathematicians for other mathematicians, or computer scientists that were actually mathematicians in disguise. And they let you do marvelous things, but they were very unapproachable. The main methodologies I used at that time that were approachable came from Derek Coleman at Hewlett Packard. There's a methodology called Fusion, which was great, in part because it let you write systems engineering models that had meaning, because it had predicates as a first order construct, and you could write things like pre and post conditions. And the business object notation, BON, from Kim Walden and Sean Nerson, which is from the Eiffel community. Eiffel's the best object-oriented programming language that lost. Um, it let you write down models and have full connections of the systems engineering models to your code. So literally in 1994, you could update your code and the models would update live, and you could change the models and the code would update live. And it's kind of like this beautiful thing everyone ever wished for, even though it existed in the 90s for a great programming language that lost to C++. And in those days, I was asking myself, well, how do you write down descriptions of complicated component-based distributed systems in a way that engineers could use? I wanted to get away from this world of people writing down mathematics. I wanted to be able to write down things that were precise but didn't taste like math. And at the time, it was exciting, but it was the wrong question because these specifications that we write not only describe the things that we mean to build, but in fact can and are being used to build the things that we mean. So systems engineering is not just like a piece of a waterfall process anymore, as you just saw with Cole's work and Andrew's work. It's a live part of a feedback cycle that goes upward from the systems engineering all the way up to normal everyday English, and downward, in my case, literally all the way down to source code, object code, and hardware design that is formally verified and traceable. So in order to achieve that goal, there's a whole lot of research work that exists that's inspirational, that you can rely upon, that it formed our thinking. I've listed a bunch of the names that influenced me here so that those of you who have been around the block can get excited about seeing an old name, or maybe new timers can say, I wonder what Daniel Jackson did, or I wondered what Cliff Jones did. These are sort of the main people who worked on the, in some sense, forgotten formal foundations of that which is systems engineering or product line engineering today, because now we have so many new tools and languages that have been built that are essentially software engineering artifacts, but in most cases are completely decoupled from the academic history in which they come from. And this is, not surprising. People like to build new things and all that kind of thing, but you're missing out on a lot if you're not understanding those semantics that exist and can be relied upon in order to design and build systems that you deeply understand. Some of the methodologies that have existed over the years that help you put systems engineering into a bigger context have also evolved over time. And the kind of method or language lineage that most strongly influences Sigil Logic's product today is down at the bottom. It's using tools and formal methods like Alloy and B and Mod and the OBJ family and the like underneath the scenes in such a way that the software engineer, a hardware engineer, or systems engineer never sees them. Where you do begin to see sort of the rigor percolate out is in things like having annotations on your source code that describe what your code means to do. Most people write that in English. Most people write it poorly, but now there's a means by which to translate between that English and the formality and hide it in such a way that you can get things like automated test generation and formal verification. We have languages like EBON and Lando that are high-level structured system specification languages that look like English. So you just feel like you're writing English and you can talk to other people and they know nothing about formal methods, but all that gets translated into formal representation. And then kind of sitting right at the middle of every project that we do is a systems engineering model. That's sort of the the fulcrum that sits right at that transition phase from high level, hand wavy, fuzzy stuff that you might see in a slide deck down into something that's more concrete, but not directly coupled to a programming language. And so we use SysML version 2, and we use a language called AADL for that. AADL has been around for a long time. It's mainly used for describing uh, important embedded systems is the way I would describe it. There's a variety of folks behind it. It's a international SAE standard, and the people doing amazing work on it are my friend Jerome Hughes at Galois, who has responsible over the years while he was at Carnegie Mellon's Software Engineering Institute for managing the main tools that sit around AADL. It's sort of the sister of Seaside. And then my colleagues Robbie and John Hatcliffe at Kansas State University, who working with Collins Aerospace, have developed a remarkable set of tools that let you reason about AADL models and generate formally verified code from said models. Now, that crew that I work with has now moved to and is using SysML2 at the same time. So we use SysML2 as a way to describe high-level systems engineering models. And in those occasions where you're building a very important cyber-physical system, that is to say something that has bent metal and uh, PCBs and moves or flies or goes in space, then you also use AADL. And that tandem is what's particularly powerful. I will mention that this work that's going on at Kansas State and Galois and the like is all funded by the government. This is government funded work that I used to be responsible for, but now I've left Galois, and is mainly funded by entities like DARPA. Now, where are we today? I want to give you kind of a snapshot of what is possible. And you've gotten a peek about that in other talks, both this year and last year. And where we're going with this with Sigil. Um, so the 30-year question that we've struggled with is, can we make rigorous engineering that uses these fancy formal methods, that is to say mathematics and logic, to literally reason about your programs, approachable by normal human beings? Like you don't have to be a PhD to do it. That's been the arc of my career. I've been building tools now for just shy of 30 years that are formal methods tools that do all kinds of fancy math, but they feel like and they taste like normal, boring compilers. They feel and taste like normal static checkers. In fact, if you're using a number of programming languages out there in the world, things like Java and C Sharp and other things, Spark, Ada, you're actually using our work. It's part of that tooling. And so for 30 years, we were trying to do this kind of rigorous formal methods with um, rigorous engineering with formal methods, but it was really hard. It wouldn't scale. It worked partially, it worked on small systems, and it required teams of experts. Literally, my average sized and nature of team that has worked with me on these topics for the last 20 odd years is between 3 and 50 PhDs who are tackling some of the most remarkable, advanced, exciting things in the world. A lot of it classified, some of it unclassified, but it required a lot of talent, a lot of background, a lot of learning. And about 5 years ago, I started putting together large language models and formal methods tools, and various folks got excited about that in the government, and it changed my life. It made me realize that I could live in a science fiction novel every day, wherein we could do rigorous engineering on behalf of and for normal engineers, and I wouldn't have to hire a bunch of PhDs. And moreover, all of you wouldn't have to hire a bunch of PhDs in order to do this. Not everyone can be Amazon and hire 200 of the best scientists in the world to do formal methods for them, or hire Galois for that matter. Instead, we can build a system that uses autonomous AI agents that are highly trained and tuned to do the formal methods on your behalf and then hide all the formal methods. So in 2026, the new answer is yes, we can do this, and on real systems with real world programming languages, with real world scale, with AI agents that we fundamentally, which are based on LLMs, which we fundamentally do not trust. We don't trust a darn thing they do. They are expensive, marvelous contraptions of science fiction. And yet, by virtue of the fact that I can put it together with tools built by smart people over the years that are hand tuned to reason about things with rigor, I can now not care about the fact that I distrust the LLMs. It's sort of no different than having a team where I have some junior engineers on the team and they're still learning the tools and techniques of the trade. And when they ask me for advice or they check in on me with their work, I have to literally come at it from the point of view of distrust because they are new and they're learning. And moreover, they might be a plant from a nation state, and I got to make sure that they're not doing a bad thing to my national security system. So what this looks like today as a foundation is firstly, we've always needed a systems engineering language that you could actually put in a version control system and wasn't proprietary and didn't have a bunch of awful extra hooks and proprietary extensions and made you feel like you were using a tool built in 1996. I'm not, I am slandering various companies here because I've had to struggle and use their tools on important systems for years, and they were awful, awful captured marketplace with awful tooling in my perspective. So when SysML version 2 first appeared, and we saw that it was trying to learn lessons of the past and it had actual concrete textual notation and more, I got excited about that fact, I must admit. Now, in the earliest days of SysML2, I did try to sit down and not just learn the language, but I tried to mechanize the semantics of the language. That is to say, write down its meaning. I used a theorem prover called PBS for that for a few weeks. I did it all by hand. And I quickly learned that early versions of the language weren't ready for formality. We were all figuring out what it meant to even build a systems engineering model in the modern age, to build an API associated with it and more. But, as the standard was evolved and developed over time, it's gotten to a better place. It's now ready for a place where we can have some mechanization of the semantics of the language, so that this coupling that you saw as an example in, for example, in Andrew's tooling, or what you might have seen last year in like P1's tooling, cannot just be, sort of ad hoc URLs or text for traceability. They can be real relations in a logical fashion, connecting together everything from an English requirement to its formal interpretation as a requirement, to a proposition that you're going to state about an architecture, to a proposition that you then state about code that you can generate a proof for, and the proof is the evidence, and it's all tied together. So Seaside is an excellent foundation for this. We've been using it on several projects in order to experiment with it, build things around it, help make it better, give feedback to the gang at Synsmetry. And it is sort of the core of the systems engineering developer experience in our tooling. And that means that we can have it sit at the core of this overall engineering method in a way that is attractive, especially to customers in the world who are moving from things like SysML1 using things like Cameo over to SysML2, and the proliferation of tools supporting SysML2, my favorite of which being Synsmetry. So the methodology we use that ties all this together is these days called Ninja. It's kind of a funny name, but it's a name because I published a series of papers over the years called Secret Ninja Formal Methods. This idea that you can hide all the formality from normal engineers. And so we decided to ride that particular jokey name. We feel like we can do that because it's literally written into recommendations made to the White House by virtue of my work on various interesting places in government. And if you talked about ninjas at the White House, then you can talk about them in my product. It gives you a refinement chain, so literally a formal connection between engineering intent expressed in English all the way down through every model in some sense that you should have learned about and used in practice by virtue of doing a computer science degree without having to know it. An example of this is like, I taught classes for years on foundations of computer science, and I would teach people about state machines, automata, regular languages, and such. And you would say, yes, every time you're going to do a state machine in code, you should probably write down the state machine first and reason about it, make sure it's the right one, minimize it, and then turn it into code. But of course, that's not how the world works. Well, now the world can work that way because this tooling does it. This is an example chain, essentially going from a high level domain down to things like formally verified Rust and Verilog and such. And just to give you a peek as what's going on, we have a SysML version 2 pack in the product. We have parameterized models like you just saw from Sysmetry. We have a mechanization going on for the semantics of SysML2 and a number of different products that use SysML. And there's a number of case studies out there in the world that you can learn from. This is one from Free and Fair called Vote Secure. It is open source. You can go download it. It has one of the richest SysML2 models that exists and describes a high assurance cryptographic voting system. And then there's other examples like the Hardens example I did at Galois, which is for nuclear power protection systems. And it too has a SysML model that connects to various facets of formal methods. So I would just wrap up saying, like where the world is today is that we can do systems as code at agent speed, just like we saw others experimenting with and using, like our friends at Anduril. And it means like right now we can move from that world of doing round trip, what I would call software engineering meets testing, to a world where we can do software, firmware, hardware, and systems engineering with formality now that we've been building our product and it's available to friends and family here in this spring. So, there's lots of folks doing this. I appreciate the work of others. Sysmetry's tooling has been instrumental in our work. We've seen excellent work going on in the defense industrial base, not just from Anduril, but others that I work with, like Collins. And our friends at P1 AI are doing amazing work on this from a mechanical and electrical engineering perspective. So just to wrap up, what we really need is to lean into SysML2 and make it better, lean into the use of tooling like which we have from Sysmetry and Seaside and other and such, because we don't need another walled garden like we had in the past. What we need is to move to a world where we have correct and secure code as a public good, which we understand by virtue of the fact of having high-level descriptions in languages such as SysML2. So that's what I have to say today. If you want to learn more, reach out. You can find us online, etc. And there's tons of public case studies.